Testing, can you hear me? Okay, this stream is public now. So I'm going to be studying discrete math again. I'm going to start studying from where I left off last time. So last stream I studied about polynomial sequences. Like there's an arithmetic, it's like an arithmetic sequence, but 2 layers deep. And the next chapter would be exponential sequences. You have a large collection of 1 by 1 squares and 1 by 2 dominoes. You want to arrange these to make a 1 by 15 strip. How many ways can you do this? What if the squares come in 3 different colors and the dominoes come in 4 different colors? And why is this second question easier than the first? Okay, I don't know what they're asking. Large collection of 1 by 1 squares and 1 by 2 dominoes. Want to arrange these to make a 1 by 15 strip. Okay, hold on. 1 by 15 strip. So we have 1 by 1 square and 1 by 2 dominoes. Let's represent dominoes like this. And they said 1 by 15 square, right? 1 by 15 strip. So we have 1, 2, 3, 4, 5, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 1 by 15 strip, 1 by 1 squares, and 1 by 2 dominoes, right? So you can place a domino here. Sorry, we can have like 15 1 squares, 15 1 square, 15 S for square, D for domino. Or you can have, okay, a single domino. Wait. So 15 squares We can have one domino. We can have like one of this being domino and the other 13 being squares. So this is one way to arrange this. Uh, one domino, 13 squares. I will type 0 domino. 0 domino, 15 squares. There are, yes, there is one way to arrange that. One domino, 13 squares. Well, so you can have a domino here. 1, 2, 3, 4, 5, 6, all the way till 1 to 14, all the way till 14, right? So there are 14 ways of doing this. There, like a pen. 14 ways of doing this. K for pen, K for laser. Okay. Now, two dominoes, 11 squares. We have this, plus this. So 1, 2, 3, 4. Yeah, this is really difficult. So first, this will happen. There are 11 squares, right? This will happen. One, two. This will happen 10 times, right? Yeah, that will this first one will go down 10 times. Once it happens 10 times, bring this once down once, and then it will happen 9 times. Bring this down once, and then it will happen 8 times. So 10 plus 9 plus 8, all the way till 1. I think that's the answer. Is this 10 correct? Is this 10 correct? So the first one, there are 15 squares, 2 taken by this, so there are 13 squares. 2 take 13 squares. 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, there are 13 squares, right? 13 squares to move around. So it actually starts with 12. So that will happen 12 times, and then push this down once. And then there are 11 spaces to move. Push this down 10. Push this down one more time, and then there are 10 spaces to move, like that. Let me think about this. 3 dominoes. I don't see a pattern. 3 dominoes. So 15 minus 2, minus 2, minus 2, 9 squares. Nine squares, 1, 2, 3, 4, 5, 6, 7, 8. How is it 10? 15 minus 2, minus 2. Then minus 2, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 13 spaces to move here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, I'm right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 9 spaces to move. Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10. Okay, I guess that makes sense because this is 14, this is 12, this should be 10. So what we need is shift this one back, and then there will be 9 spaces to move. And then this goes here, and then there will be 8 spaces to move all the way till 1. All the way. So the one case is here, right? Here's the thing. You bring this one block down, and then you restart the entire thing again. So now you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Then there is 9 plus 8 all the way till 1. 8 plus till 1. Yeah. Then you're left with this. This would be sum from 10 to 1. From 1 to 10. Actually, and like that. Sum from 1 to 12. But I'm not seeing any pattern though. If I have 4 dominoes and 7 square, then it will be 8 all the way till 1 plus 1, right? The fourth domino will go from 8 to plus 1. From 8 to 1. And then this will be shifted 1 down. This will be shifted 1 down. And then we do 7 to 1. Okay, so we have from there, from 8 to 1, then 7 to 1, then 6 to 1. Okay, forget this. I'll just read the chapter. Consider the Fibonacci sequence. Gradient. They said to consider a recurrence relation. Consider the Fibonacci sequence 0, 1, 1, 2, 3. We look at the first differences, we get this sequence 1, 1, 2, 3, 5, 8, which is the Fibonacci sequence itself. This is not surprising since the Fibonacci sequence is defined by the recurrence relation. That is saying precisely that we need to go to the next term of the sequence. We take the current term and add a term in the sequence. Of course, if we take another difference, we'll get the same sequence back. And again, so no nth difference will be constant. Another sequence that has this behavior is the powers of 2. Powers of 2, which has differences 1, 2, 4, 8, 16, 32. You can also see this from the recurrence relation since an is equal to 2 an, which is an 1 plus an 1. The rate of this growth, the rate of growth for this, and in fact any geometric sequence, is the sequence itself. If you studied calculus, you may recall that the functions that have themselves as a rate of change are exactly the exponential functions. So consider the recurrence relation in n is equal to 5a n minus 1 minus a n minus 2. Since the n term is given as a combination of two previous terms, we need two initial terms to determine the sequence. Different initial terms will give different sequence. What sequence do you get if the initial conditions are a0 is equal to 1 and a1 is equal to 2? Give the first five. Give the first 5 terms. Okay, so 1, 2. So what do they say? Um, can I use decimals for this? F of 0 is 1. F of 1 is 2. F of n by n minus 1 plus it with 6 f n minus 2. So does this work? F of 2. Let's just manually check it. So they want A3, 5, A2 minus 6, A1. 6 times 2 is 12. Sorry, 5 times 2 is 10. Then minus 6, which gives 4. 5 of 3 is 8. 8 and then 16. Based on the first few terms, what is the closed formula for this sequence? 2 to the power of n. What sequence do you get if the initial condition are A0 is equal to 1 and A1 is equal to 3? So we have 139, 139, 139, 81. 243. I missed 27. Based on the first few terms, what is the closed formula? 3 to the power of n. Uh, yeah, A0 is 1, A1 is 3. So A2 is 3 squared and then 3 cube and then 3 to the power of 4. 2 and 5. 5. 2, 5, 13. 2, 5, 13. 35. 97. 2, 5, 13. 35. So if I subtract 1, yeah, if I subtract 1, I get 1, 4, 12, 34. I don't think that's any use. Is it 2 square? No, not 2 square. 2, 2 times 2, 2 times 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 2 times 2. So 1 plus 1, 2 plus 3, 4 plus 9 is 15. Sorry, 4 plus 9 is 13. So it's 2n plus 3n. Why does this work? Suppose a candy machine dispenses candy in a geometric sequence by first giving one candy, then two, then four, then eight. How many candies will you have received in total after 10 turns? We can create the sequence of partial sums as 1, 1 plus 2, 1 plus 2 plus 4, 1 plus 2 plus 4 plus 8. That gives 1, 3, 7, 15, 31, 63. This is not a geometric sequence, but it is almost. In fact, if we add 1 to each term, we get what sure looks like the geometric sequence 2, 4, 8, 16, 32. So we might guess that the closed formula for the sequence of sums is 2 to the power of n plus 1 minus 1. If this is correct, then the answer to the candy question would be 2 to the power of 11 minus 1. It's 2047. More intriguing, though, is the observation that the sequence of partial sums of geometric sequence is again geometric. Let's consider how to find the sum of a geometric sequence in general. Okay, a geometric sequence. Should I start with A0 or A1? I'll start with A0. But then we end up with, I'll start with A1. So we can end up with AN as the last term. So first term, I will call it A. And in a geometric sequence, the next term is like multiplied with R. So it's like AR, then AR square, N minus 2, N minus 1. So the sum is A plus AR plus AR square plus ARN minus 2 plus ARN minus 1. R times S is AR square, AR cube, N minus 1. S minus RS. So I'm subtracting these two. But the thing is, uh, hold on. This and this will cancel out. This and this will cancel out. This and the AR cube in here will cancel out. And then AR n minus 2 will cancel out. And then this and this will cancel out. So we are left with A plus AR n. Sorry, minus AR. It's A plus AR minus AR plus AR square minus AR square. So on, yeah. So this is the sum. So what they're asking, example 4.4.1, A is equal to 3, R is equal, R is 3, right? R is 3 times 2 times 2 times 2, R is 2. Um, Rn is equal to 12288, 88, 2 to the power of n, 88 over 3, 12288. Four zero nine six. Is that 2 to the power of 8? Nope. 8, 10, 12, 12. So there are 12 terms in total. So the sum is 1 minus 2 to the power of 12. Oh, I never needed to do this. I can just use this. 1 minus 2. So 2 to the power of 12, 4096 minus 1 times 3, 2 minus 1. 12285. I never needed to do 2 minus 1 because that's 1. I can like multiply this with, I can multiply both sides with minus 1. So I can have a positive thing. So I don't have minus on the top and bottom. To better see what happened in the example above, we can write in this way. Find a closed formula for Sn. Okay, we already know how to do that. 2, 5, 5, 5. Okay. Even though this might seem like a new technique, you've probably used it before. 0, 4, 6, 4, 6, 4, 6. 4.4.3. We represent it like this, right? Recurring relations. So this is equal to x is equal to 100x. So 100 minus x is 99. X is equal to 46. Yep. Suppose we want to solve a recurrence relation expressed as a combination of two previous terms, such as an is equal to an minus 1 plus 6 an minus 2. In other words, we want to find a function of n which satisfies an minus 1 minus 6 times an minus 2 is equal to 0. Think about how we build up the sequence iteratively. And this. Let's stop there and agree this is getting very complicated. However, we do notice that in each step we would, among other things, multiply a previous iteration by 6. So a closed formula would include 6 multiplied by some number of times. Thus, it is reasonable to guess the solution will contain paths that look geometric. Perhaps the solution will take the form r to the power of n for some constant r. The nice thing is we know whether to check whether a formula is actually a solution to a recurrence relation. Plug it in. What happens if we plug in r to the power of n into the recurrence above? We get r to the power of n. Okay, so by factoring r is equal to -2 or r is equal to 3, this tells us that an is equal to -2 to the power of n is a solution to the recurrence relation, as is an is equal to 3 to the power of n. Which one is correct? They both are, unless we specify the initial condition. Notice that we could also have an is equal to -2 to the power of n plus 3 to the power of n. They said factoring r is -2 or r is 3, right? Okay. In fact, for any a and b, an is equal to a -2 to the power of n plus b times 3 to the power of n is a solution. To find the values of a and b, use the initial conditions. This points us in the direction of a more general technique for solving recurrence relations. Notice we will always be able to factor out r to the power of n minus 2 as we did above, so we really only care about the other part. We call this other part the characteristic equation for the recurrence relation. We are also interested in finding the roots of this characteristic equation, which are called the characteristic roots. Given a recurrence relation, an is equal to alpha an minus 1 plus beta an minus 2, the characteristic polynomial is x square plus alpha x plus beta. X square plus alpha x plus beta. Okay. No, wait a minute. Why are we replacing an by x square and an minus 1 by x and an minus 2 by 1? Giving the characteristic equation x square plus alpha x plus beta is equal to 0. If R1 and R2 are two distinct roots of the characteristic polynomial, then the solution to the recurrence relation is an is equal to a times Rn1 plus Prn2. Where a and b are constants determined by the initial condition. Oh, this is the last part. I mean, how do they get this? I need a more clear proof of why they're doing this. Perhaps the most famous recurrence relation is Fn plus Fn minus 1 plus Fn minus 2, which together with the initial condition F0 is equal to 0 and F1 is equal to 1 defines the Fibonacci sequence. And notice this is precisely the type of recurrence relation on which we can use the characteristic root technique. When we do, the only thing that changes is that the characteristic equation does not factor, so we must use quadratic formula to find the characteristic roots. In fact, doing so gives us the third most famous irrational number, the golden ratio. Before leaving the characteristic root technique, we should think about what might happen when solving the characteristic equation. You have an example above in which the characteristic polynomial has two distinct roots. These roots can be integers or perhaps irrational numbers. In these cases, we know what the solution to the recurrence relation looks like. However, it is possible for the characteristic polynomial to have only one root. This can happen if the characteristic polynomial factors as x minus r square. It is still the case that r to the power of n would be a solution to the recurrence relation. But we won't be able to find solutions for all initial conditions using the general form a n is equal to a r n plus b r n, since we can't distinguish between r1 and r2. We are in luck. Suppose the recurrence relation a n is equal to alpha a n minus 1 plus beta a n minus 2 as a characteristic polynomial with only one root r, then the solution to the recurrence relation is. I want proofs of this. Notice the extra n in b and r to the power of n. Okay, I think I will try to look for proofs of this off stream and try to end the stream here then. Okay, I will continue with the next topic, which seems to be on induction next stream. And yeah, I will see you guys next time. Bye.